In the cold, dark expanse of our solar system, a strange phenomenon occurs on certain ice giant planets. Diamonds rain down as precipitation, falling from the sky like frozen crystals. This discovery was first made in the 1980s when spacecrafts flying by Uranus and Neptune detected these precious gemstones within their atmospheres. Scientists were baffled by this revelation, as diamonds are typically formed under intense heat and pressure deep within the Earth's mantle. However, on ice giants like Uranus and Neptune, the extreme temperatures and pressures in their lower atmospheres create conditions where carbon atoms can bond together to form diamonds. These diamonds then fall as rain to the dense, icy atmosphere of these distant worlds. Imagine witnessing this incredible phenomenon firsthand, a sky filled with sparkling diamonds falling like snowflakes. The mystery of diamond rain continues to captivate scientists and astronomers alike, driving further exploration and research into these enigmatic ice giants. As our understanding deepens, the wonders of our solar system only become more profound and extraordinary. The next time you look up at the night sky, remember that on some distant worlds, it rains precious gems from above. Before we begin, a small request. Most of the people listening tonight aren't subscribed. If this channel has ever helped you drift off, take a moment to subscribe. It's free. It helps this channel more than you'd think, and you can always change your mind later. And if you feel like it, leave a comment telling me where in the world you're listening from and what time it is where you are. I love reading them. One more thing before we begin. I'm also a co-founder of a sleep app, built to be the most affordable one out there. No ads, ever. Just sounds and stories made to help you sleep. It may not be released yet as this video goes up, but if you're watching a little later, it might be out by now. Just search for it, it should be easy to find. It works on iPhone, Android, and everything in between. Downloading it is the best way to support this channel. On the ice giant planets of our solar system, extreme conditions exist that allow diamonds to form and fall like rain. Consider Uranus, discovered by William Herschel on March 13, 1781. It experiences extreme temperature variations, ranging from 27 degrees Celsius (C 358 degrees Celsius) at the poles to -7 degrees Celsius at the equator. These temperatures, coupled with Uranus's unique magnetic field, which is tilted and offset from the planet's center, create an environment where diamonds can form. The combination of extreme temperatures and pressures in Uranus's atmosphere allows for the transformation of carbon into diamonds. As a result, it is believed that diamonds can precipitate out of Uranus's atmosphere and fall like rain on the planet's surface. These extraordinary conditions on ice giants like Uranus reveal how diamonds can fall as rain in our solar system's most distant worlds. Understanding these unique atmospheric conditions deepens our appreciation for the remarkable processes that occur on ice giants like Uranus. In the cold, distant realm of ice giants like Uranus, a fascinating process unfolds that captures the imagination and defies our everyday understanding of reality. Under extreme conditions, carbon atoms coalesce and form tiny, brilliant diamonds. This diamond rain is a testament to the unique atmospheric conditions of these ice giants. Let's delve into the formation process that makes this phenomenon possible. To begin, carbon atoms need an environment where they can bond under intense pressure and heat. In Uranus's atmosphere, these conditions are met in its lower layers. Here, the temperature can reach up to 1,000 degrees Celsius and pressure levels that exceed 5,000 bars, equivalent to the weight of 5 elephants standing on a single square inch. Under these extreme conditions, carbon atoms from methane gas molecules begin to bond together. This process is known as nucleation, a critical step in the formation of diamonds. Once the initial bonds form, other carbon atoms are drawn in, creating a cascade effect where more and more atoms join the growing diamond seed. Over time, These tiny seeds of diamonds grow larger as they fall through Uranus's atmosphere, picking up speed and momentum. They become what we commonly refer to as diamond rain. Imagine standing on the surface of a distant world, gazing up at this extraordinary spectacle, tiny diamonds raining down from the sky, each one born under intense pressure and heat. This celestial event is a stark reminder of the incredible processes that occur in the vast and mysterious realms of our solar system, far from the familiar and mundane experiences of everyday life on Earth. To witness this firsthand would be a humbling experience, a glimpse into the raw power and elegance of nature's most extraordinary phenomena. To witness this firsthand, scientists rely on advanced tools and techniques to observe the distant ice giants of our solar system. But let's be clear, observing diamond rain is no easy task. Remote sensing, using powerful telescopes and spacecraft, allows us to gather data from these far-off worlds. However, the distance and harsh conditions make direct observation challenging. Even with state-of-the-art technology, resolving details like falling diamonds on a planet light years away is incredibly difficult. Theoretical models come into play here, helping us understand what might be happening on these planets based on known physics and chemistry. For instance, the extreme pressures and temperatures within Uranus could indeed lead to the formation of diamonds. Although no confirmed observations of diamond rain have been made yet, scientists are constantly refining their methods and tools to gain better insights into these enigmatic worlds. What we do know is that Uranus's mass of approximately 8.683 tons 1025 kg contributes to the planet's unique internal structure, which might facilitate this extraordinary phenomenon. Despite the hurdles, the allure of unraveling these celestial mysteries keeps scientists pushing forward. For now, we continue to piece together the puzzle, eager for future discoveries that might reveal more about this awe-inspiring natural phenomenon. Take the Europa Clipper mission, for example. Set to launch far in the future, this spacecraft will conduct a series of flybys around Jupiter's moon, Europa, which is believed to harbor an immense subsurface ocean. The primary objective of this mission is to study the composition and habitability of Europa's vast liquid water reservoir, which might provide clues about similar conditions on other ice giants. If we find that diamond rain occurs in such environments, it could transform our understanding of how planets form and evolve. Meanwhile, the Uranus Orbiter and Probe mission is also in the works. Scheduled for a 2038 launch, this endeavor aims to explore the complex dynamics of Uranus's atmosphere, its intricate ring system, and the unique properties of its icy moons. Advancements in space technology are crucial for these missions. The development of more robust and precise instruments will enable researchers to gather data that was previously unattainable. For instance, high-resolution spectrometers can analyze the chemical composition of planetary atmospheres with unprecedented accuracy. As we delve deeper into these icy worlds, our understanding of the cosmos continues to expand. Each new mission represents a significant step forward in our quest to unravel the mysteries of our solar system. Imagine witnessing these phenomena firsthand. The sight of diamonds falling like rain on a distant ice giant planet would be nothing short of extraordinary. As we look to the future, our anticipation grows for what these upcoming missions will reveal about the wonders of our solar system. For now, we remain captivated by the enigma of diamond rain and the incredible possibilities it holds. Diamonds, known for their resilience and beauty on Earth, can also form in the atmospheres of ice giants like Uranus. But how do they come to be? Let's delve into the formation processes that lead to these gemstones raining down from above. One mechanism is through shock waves caused by intense collisions. These powerful waves can compress and heat the carbon-rich atmosphere, creating conditions suitable for diamond formation. Another pathway involves heat-driven reactions, where the intense temperatures in these atmospheres promote chemical transformations. These extreme environments enable the conversion of carbon into diamonds, which then fall as rain onto the surface below. Additionally, chemical equilibrium processes play a role in diamond formation. These processes maintain a balance between the different forms of carbon, allowing diamonds to be stable and abundant in these atmospheres. Imagine witnessing this spectacle from above, sparkling diamonds cascading down like a celestial waterfall. To truly appreciate the spectacle of diamond rain, we must delve into the planetary interiors of these icy giants and understand how they generate the right conditions. Despite their size difference, both planets share a crucial feature: immense internal heat flux. This heat is not from the sun's radiation, but rather from the gravitational energy released as these planets contract under their own weight. Imagine a hot core of liquid hydrogen and helium compressed to an incredible pressure due to the planet's massive gravity. The intense pressure within these ice giants is another key factor in diamond formation. In the deep interiors of Jupiter and Uranus, pressures can reach over 1 million times that found on Earth's surface. It's this constant rain of diamonds from above that creates the awe-inspiring spectacle we envision. As you witness this celestial waterfall of diamonds cascading down, you are truly gazing at the wonder of our universe's natural laboratories. At first glance, the atmosphere of Uranus may appear calm and serene. But beneath this deceptive tranquility lies a dynamic world of wind patterns, temperature gradients, and convective currents that shape a truly extraordinary phenomenon: diamond rain. This significant temperature difference creates convective currents within Uranus's atmosphere. These currents act like invisible highways, lifting diamonds from their formation zones and carrying them higher into the atmosphere. Imagine these tiny diamonds, no larger than a speck of dust, riding on these convective currents as if they were on an invisible elevator. As the diamonds reach higher altitudes, they encounter different temperature zones. The cooler temperatures cause these tiny carbon crystals to solidify and form into the beautiful gems we recognize. The combination of Uranus's powerful winds and convective currents creates a unique atmospheric dynamic that allows for the formation and distribution of diamond rain. The sight of these glistening diamonds falling like rain is a testament to the intricate ballet of atmospheric processes on this distant ice giant. The evidence begins with spectroscopic analyses of the ice giant planet's atmospheres. These studies have revealed signatures of methane and other hydrocarbons that are thought to be involved in the formation of diamonds. Infrared imaging also plays a crucial role in piecing together this cosmic puzzle. By studying the thermal emissions from these distant worlds, scientists can map out temperature variations within their atmospheres. Computer simulations further strengthen our understanding of diamond rain by modeling the complex interactions between carbon and other elements in the extreme conditions found on ice giants like Jupiter and Uranus. Imagine a world where the simplest of organic compounds, like methane, are subjected to immense pressures and temperatures. Under these conditions, methane can break down into carbon atoms that then combine to form diamond crystals. These diamonds, lighter than air, are believed to fall through the atmosphere like rain, creating a dazzling display of celestial gems cascading downwards. But the story doesn't end there. As these diamonds continue to fall, they eventually reach a point where the pressure and temperature conditions no longer favor their formation. Instead of turning back into methane, however, some of these diamonds might sink deeper into the planet's interior, where they could potentially play a role in shaping its internal structure and dynamics. While we may not be able to witness this spectacle firsthand, the convergence of multiple lines of evidence, spectroscopic analyses, infrared imaging, and computer simulations provides compelling support for the existence of diamond rain on ice giant planets. The thought of these precious gems falling like rain is not just a whimsical idea, but a fascinating reality supported by rigorous scientific inquiry. In the vast expanse of our solar system, two ice giants stand out for their unique atmospheric phenomena: Uranus and Neptune. Both planets are known for their intense weather patterns, but one phenomenon in particular captures the imagination: diamond rain. This isn't a figment of fantasy. It's a fascinating reality supported by rigorous scientific inquiry. To understand how this precious gem rain can occur, we must explore the role of planetary rotation. With a 98-degree axial tilt, Uranus spins on its side, creating unique weather patterns driven by the Coriolis effect. This effect causes winds to curve in complex ways, leading to atmospheric layers mixing more efficiently than on other planets. The result is an environment where diamonds can form and crystallize in the atmosphere. But it's not just about formation. These precious gems need a pathway to the surface. This is where Neptune, with its more conventional axial tilt, comes into play. Though Neptune's rotation isn't as extreme as Uranus's, it still plays a crucial role in bringing diamonds to the surface through convection currents. These currents are strengthened by Neptune's rotation, helping diamonds rise and fall like rain in the planet's atmosphere. Imagine witnessing this incredible spectacle, diamonds falling like precious rain, a result of the complex dance of planetary rotation and atmospheric dynamics. As we gaze upon these distant worlds, we see how the intricate ballet of planetary rotation can give rise to wonders beyond our wildest dreams. In the quiet stillness of space, these celestial phenomena unfold, reminding us that the universe is a place of endless discovery and beauty. Atmospheric chemistry plays a crucial role in shaping the environments of ice giants like Jupiter and Uranus. This chemical composition creates a dense atmosphere that can be up to 1,000 kilometers thick. The presence of methane leads to the formation of hydrocarbons and other organic compounds that contribute to Uranus's unique atmosphere. As lightning strikes within the atmosphere, it triggers chemical reactions that convert carbon and hydrogen into graphite and then diamonds. Trace elements and impurities in the atmosphere can also influence the quality and appearance of these diamonds. Imagine witnessing this process firsthand, the birth of diamonds falling like rain in the harsh yet beautiful environments of ice giants. The atmospheric chemistry of these planets is what makes this extraordinary phenomenon possible, a testament to the wonders hidden within our cosmic neighborhood. The magnetic fields of planets like Uranus and Jupiter are not just mere forces. They are mighty and intricate systems that shape the dynamics of these ice giants' atmospheres. Imagine the magnetic field as an invisible force field, shaping the pathways of charged particles and currents that flow through the atmosphere. This is crucial because these currents interact with the unique atmospheric chemistry that allows diamonds to form. These magnetic fields do not simply exist in isolation. They interact with the atmospheric currents, guiding and channeling them along specific paths. Think of these charged particles like tiny, glowing diamonds themselves. They move and cluster in ways influenced by the magnetic field's strengths and orientations. As a result, the visibility and distribution of diamond rain can be dramatically affected. On Jupiter, where the magnetic field is exceptionally strong, the currents might be more concentrated in certain regions. This could make diamond rain events more frequent and intense in those areas, creating a breathtaking spectacle for any observer fortunate enough to witness it. Conversely, Uranus's complex magnetic field dynamics might lead to a more scattered and less predictable distribution of diamonds within its atmosphere. Here, the interplay between magnetism and atmospheric currents could create intricate patterns that are as beautiful as they are elusive to observe. Understanding these magnetic influences adds another layer to the fascinating story of diamond rain, highlighting how planetary magnetic fields can profoundly shape the visibility and behavior of this cosmic wonder. As we explore the mysteries of our universe, these magnetic forces remind us that even invisible elements play a crucial role in shaping the phenomena we seek to understand. The optical properties of diamonds cause them to shimmer and reflect light in a mesmerizing display. As these diamond droplets tumble through the atmosphere, they catch the light, creating a dazzling cascade of brilliance. This sparkle is due to their high refractive index, how well a material can bend light as it passes through it. Imagine the size of these diamonds varying from microscopic to sand-sized particles. Each one reflects and scatters light in a unique way, creating a kaleidoscope of glittering patterns. The visual display changes with the size and shape of these diamonds. Smaller ones create a fine, shimmering mist, while larger particles produce distinct, flashing points of light that streak across the sky. Diamonds are not always colorless. Impurities can give them a tint, creating colored diamonds that add another layer to the visual spectacle. These impurities can absorb specific wavelengths of light, altering the observed spectrum. Picture a red diamond, for example. As it catches the light, it reflects back hues of crimson and scarlet, painting the sky with vivid streaks of color. The combination of these various sized, colored diamonds creates a stunning display that is both mesmerizing and otherworldly. To witness this diamond rain firsthand would be an experience beyond description. It's a sight that combines the elegance of gemstones with the awe-inspiring power of celestial bodies. This visual spectacle not only enhances our understanding of the universe, but also deepens our sense of wonder at the beauty and complexity of cosmic phenomena. On Uranus, it's not water vapor that condenses and falls from the sky, but something far more precious: diamonds. This celestial phenomenon is known as diamond rain, a stark contrast to the familiar precipitation we experience on Earth. On Earth, we are accustomed to seeing water precipitate in various forms: rain, snow, sleet, or hail. These different types of precipitation are determined by the temperature and atmospheric pressure within specific layers of our atmosphere. One of the most striking aspects of diamond rain is that it falls steadily, similar to a continuous drizzle on Earth. This steady rain is caused by the constant high-pressure conditions in these planets' interiors. Unlike Earth's precipitation, diamond rain doesn't evaporate quickly. The intense pressures and low temperatures prevent the diamonds from sublimating back into gas. Instead, they continue to fall and accumulate in the planet's core. The environmental conditions necessary for diamond rain are so extreme that they cannot exist on Earth. Our planet's atmospheric pressures and temperatures simply don't reach the levels needed to force carbon into these precious gemstones. Imagine standing under a sky filled with glittering diamonds, each one a tiny gem falling steadily to the planet's surface. This otherworldly sight is a testament to the incredible diversity and complexity of phenomena in our universe. And remember, while we may never get to witness this celestial diamond rain firsthand, every gemstone you see is a tangible connection to the wonders of the universe, reminding us that there are still many mysteries waiting to be discovered. In the frigid depths of ice giants like Uranus, an unusual phenomenon occurs. It's called diamond rain. Here, carbon atoms swirling in the atmosphere form tiny solid crystals that fall like raindrops. But how do these carbon atoms end up in the atmosphere of an ice giant? The answer lies in the unique carbon cycle that operates on these distant worlds. Unlike Earth, ice giants don't have a steady supply of carbon from volcanic activity. Instead, the carbon in these planets' atmospheres comes primarily from methane and other hydrocarbons. The extreme cold of these ice giants causes the methane to break down, releasing carbon atoms into the atmosphere. Imagine the scene: millions of microscopic diamonds raining down through the dense atmosphere. This process is vastly different from Earth's carbon cycle, where carbon is recycled through living organisms and geological processes. Witnessing this celestial diamond rain firsthand is a breathtaking reminder of the unique wonders hidden within our solar system. Deep within the ice giant planets of our solar system, a phenomenon unlike any other takes place. Diamond rain showers these celestial giants in a cascade of precious gems, forming under extreme pressures and temperatures. But the question that intrigues scientists and dreamers alike is, Could there be life in these harsh environments where diamonds rain from the sky? Extremophile organisms, capable of surviving in extreme conditions, offer a tantalizing glimpse into this possibility. These tiny creatures thrive in environments that would be lethal to most life forms. Their resilience is a testament to the adaptability of life. Imagine microscopic organisms withstanding the intense pressures and temperatures within Uranus's atmosphere, where diamond crystals form under the immense weight of the planet's dense layers. Scientists speculate that certain bacteria or other microorganisms could potentially survive in the liquid hydrocarbons found within these planets' atmospheres. The idea of life persisting in such hostile environments challenges our understanding of what is possible for living organisms. Now, imagine, if you will, the extraordinary phenomenon known as diamond rain. In the intense pressure and heat of Jupiter's interior, carbon atoms combine under immense forces to form tiny diamonds. These diamonds then sink deeper into the planet's core, where they might eventually merge with other solid materials, creating unique and complex chemical compositions. Similar to Jupiter, Uranus experiences immense pressure and heat within its core. This environment is also conducive to the formation of diamonds, which might then rise up towards the planet's surface. The impact of these diamond fragments on Uranus's icy mantle could have significant geological consequences. They might cause localized melting and even small-scale volcanic activity. While these events are likely to be subtle and scattered, they could leave behind unique chemical signatures or surface features that might be detectable from a distance. Despite these advancements, our understanding of ice giants and diamond rain remains largely theoretical due to the extreme conditions involved. Imagine witnessing this extraordinary natural phenomenon firsthand, the slow but steady descent of diamonds through an alien atmosphere. This is not mere science fiction, it is a genuine process happening in the depths of our solar system's most mysterious worlds. As we continue to explore these distant worlds with advanced technology, we may one day observe the impact of diamond rain on their surfaces more directly. In our solar system, there exist ice giants like Uranus, which, due to their extreme tilt, experience planetary seasons unlike anything on Earth. These drastic temperature changes influence the formation of diamond rain on Uranus. The intense sunlight at the pole facing the sun and the lack of it at the other pole creates starkly different conditions that affect how diamonds form. As Uranus transitions through its seasons, the frequency and intensity of diamond rain can vary significantly. Imagine a world where diamonds fall like rain during certain times of the year, creating a unique and spectacular phenomenon. These variations in diamond rain are a fascinating example of how planetary seasons can impact geological processes on ice giants like Uranus. Understanding these seasonal dynamics deepens our knowledge of how diamond rain works and its role in the broader context of planetary environments. But the diamonds that form in these extreme conditions aren't like those we find on Earth. They come in a variety of compositions and impurities that tell a fascinating story about the chemistry and history of these distant worlds. One of the key variations in diamond rain is the differing carbon isotopes that can make up these crystals. Carbon exists naturally in several forms, or isotopes. On Earth, the most common is carbon-12, but in these gas giants, carbon-13 and even heavier isotopes can be more prevalent. This variation arises from the unique atmospheric conditions of Uranus and Neptune, where different processes shape the composition of the diamonds that eventually form. Adding to this complexity are the impurities that can be trapped within these diamond crystals as they form. These tiny inclusions offer scientists a window into the planetary environment from which they hail. Imagine if you could hold one of these diamonds in your hand, a tiny speck that has traversed the atmospheres of these colossal ice giants. The presence of specific impurities can reveal details about the conditions under which the diamond formed, temperature, pressure, and even the composition of the surrounding atmosphere. By studying these diamonds, scientists can piece together a narrative of the planetary history and dynamics at play in these distant worlds. Understanding the composition variations of diamond rain not only sheds light on the chemistry of these distant worlds, but also offers insights into the broader workings of our solar system. As we continue to explore and unravel the mysteries of these icy giants, each new discovery brings us one step closer to comprehending our universe's incredible complexity. And who knows? Perhaps one day, we might witness firsthand the awe-inspiring spectacle of diamond rain falling through the skies of these distant worlds. In the vast expanse of space, where colossal planets spin in silent orbits, lie worlds unlike our own, ice giants, enveloped by swirling storms and cloaked in veils of mystery. At their cores, these titanic bodies harbor secrets that can shape the very essence of life itself, diamond rain. But how do diamonds form within such alien environments? The answer lies deep within, where core dynamics sculpt the planet's destiny. This core is not just a passive center, it's a dynamic engine that influences Uranus's magnetosphere and overall structure. The icy mantle, with its swirling currents of methane and other elements, interacts with the magnetic field generated by the core. Now, picture the intense pressure and heat within this icy mantle. As temperatures soar, conditions become ripe for chemical reactions that would be unimaginable on Earth. Carbon atoms, subjected to these extreme environments, begin to bond together in unique ways. These bonds form the basic building blocks of diamonds. As carbon atoms combine under immense pressure and heat, they crystallize into the hardest known substance in the universe. But how do these tiny diamonds make their way to the planet's surface? The answer lies in the peculiar dynamics of Uranus's core. As the core rotates at an angle to the mantle, it generates currents that drive carbon-rich materials upward through the icy layers. When these carbon-laden fragments reach cooler regions of the atmosphere, they release their precious cargo, diamonds that rain down like sparkling meteors through Uranus's alien skies. This breathtaking phenomenon is a testament to the power of core dynamics in shaping a planet's fate. It reminds us that beneath the surface of even the most distant worlds, complex processes are at work, sculpting landscapes and phenomena beyond our wildest dreams. Underneath the surface of many ice giants like Uranus and Neptune, conditions are ripe for a fascinating phenomenon, diamond rain. At pressures more than 1,000,000 times greater than those found on Earth's surface, the carbon in these planets can solidify into diamonds. These tiny, brilliant gems then fall through the planet's atmosphere like precipitation, a process aptly named diamond rain. Now, consider the potential ecological implications of such a phenomenon. On Earth, the carbon cycle is fundamental to life as we know it. But on these ice giants, carbon takes on a completely different form. The diamonds falling from the sky could potentially serve as a unique nutrient source for hypothetical life forms adapted to these extreme conditions. Imagine organisms that have evolved to absorb or consume diamonds as part of their metabolic processes. Diamond rain might even play a role in the development of complex ecosystems, with different species adapted to utilize this unusual resource. While we can only speculate about such alien ecologies, the existence of diamond rain expands our understanding of the diversity and complexity of planetary ecosystems. Neptune, the 8th planet, is also an ice giant and shares a similar blue hue due to the presence of methane in its atmosphere. Both Uranus and Neptune are believed to have rocky cores surrounded by layers of water, ammonia, and methane ices. At extreme pressures within these ice giants, the ices transform into a supercritical fluid with remarkable properties. This unique state allows for the formation of unexpected substances such as diamonds. Imagine witnessing this cosmic phenomenon firsthand, a steady rain of diamond crystals falling through the supercritical fluid environment within these distant worlds. This captivating process, known as diamond rain, is a testament to the extraordinary diversity and complexity of planetary ecosystems in our solar system. As we continue to unravel the mysteries of these ice giant planets, we gain a deeper appreciation for the wonders hidden within our own cosmic backyard. In the next chapter, we will delve into the fascinating science behind this remarkable phenomenon and its implications on our understanding of planetary systems. The atmospheric layers of ice giants like Uranus play a crucial role in the formation of diamonds. Let's explore how these layers contribute to this extraordinary phenomenon. The troposphere is the lowest layer where most weather occurs. It extends from the surface up to about 60 kilometers in altitude. This layer is rich in hydrogen and helium, with traces of methane that give Uranus its distinctive blue color. The stratosphere lies above the troposphere, extending from about 60 to 480 kilometers in altitude. In this layer, methane breaks down under the influence of sunlight, creating complex hydrocarbons that contribute to the formation of diamonds. The thermosphere is the uppermost layer, extending from about 480 to 10,000 kilometers above Uranus's surface. Here, the hydrocarbons produced in the stratosphere are exposed to intense solar radiation and extreme temperatures. These conditions cause the hydrocarbons to crystallize and fall as diamond rain into the layers below. Methane, an abundant gas in the atmosphere of ice giants like Uranus, undergoes a fascinating process known as methane breakdown. Under the intense pressure and heat of Uranus's interior, methane molecules begin to break down into simpler hydrocarbons. These hydrocarbons then undergo further transformation, eventually leading to the formation of pure carbon. The high pressure and temperature conditions cause this carbon to crystallize into diamonds. These diamonds, too heavy to remain suspended in the gas, fall like raindrops through the layers of Uranus's atmosphere. Imagine witnessing this spectacle from within the dense clouds of Uranus, a cascade of sparkling diamonds. As they tumble downwards, these precious gems accumulate in the deeper layers of the planet's atmosphere. This incredible process of methane breakdown and diamond formation offers a glimpse into the extraordinary chemistry happening deep within ice giants like Uranus. And while we may never witness this cosmic phenomenon firsthand, understanding the science behind it adds to our awe and wonder of the universe's rich tapestry. Imagine the chaotic dance of diamonds as they cascade down through Uranus's turbulent skies, glittering like shattered glass in a cosmic storm. As carbon atoms from methane gas deep in Uranus's atmosphere cool and solidify, they form tiny crystals of diamonds. These precious gems then fall as a relentless rain, pummeling through the thick atmosphere and altering the planet's atmospheric composition in the process. The heat generated by the diamonds as they plummet through the atmosphere leads to significant temperature changes. The resulting storms are so intense that they sculpt the planet's upper atmosphere, shaping it into a complex system of bands and currents. Witnessing such a spectacle firsthand would be an astounding sight. The sky alight with shimmering diamonds, the air crackling with the force of these unseen storms. This cosmic ballet is a stark reminder of how interconnected the elements are, and how even the smallest components can reshape an entire world. Understanding diamond rain not only adds to our awe of the universe, but also highlights how even the most minuscule processes can have profound planetary consequences. At the very core of ice giants like Jupiter and Uranus lies a complexity that sets them apart from other planets, their intricate carbon cycle. Jupiter's Great Red Spot is not just a massive storm, it is also a testament to the planet's turbulent atmosphere and its unique way of processing carbon. In these ice giants, carbon can descend deep into their interiors, subjected to immense pressures that transform it into graphite. As the carbon continues its journey, it faces even greater pressures, eventually crystallizing into diamonds, a process known as diamond rain. This phenomenon is not merely a celestial spectacle, it plays a crucial role in shaping the planet's interior structure and dynamics. Imagine witnessing this diamond rain firsthand, tiny diamonds falling like precious drops of liquid gold in a planetary environment so alien to our own. The carbon cycle's complexity on ice giants highlights how these processes can have profound effects on the planet's structure and behavior. Atmospheric pressure is the force exerted by gas molecules within a planet's atmosphere. It varies greatly depending on the planet and its composition. This variation in pressure can lead to the formation of something extraordinary: diamond rain. High-pressure environments can force carbon atoms to bond tightly, forming diamonds. As we continue to explore the far reaches of our solar system, these insights into how pressure influences the creation of diamond rain provide a fascinating glimpse into the wonders of planetary science. Offering insight into how pressure influences the creation of diamond rain gives us a new perspective on the incredible phenomena that can occur in our cosmic neighborhood. Understanding these planetary atmospheric pressures not only enhances our knowledge of the universe, but also fuels our curiosity about what other marvels might be waiting to be discovered. The atmospheres of ice giants like Uranus and Jupiter are akin to vast chemical laboratories, where conditions can lead to the formation of diamonds through specific chemical reactions. Within these planetary atmospheres, hydrocarbons such as methane and ethane can react with oxygen under high pressures to form heavier hydrocarbons like acetylene. This acetylene can further polymerize, creating long chains of carbon atoms that serve as the building blocks for diamonds. Under extreme conditions, these carbon chains can crystallize into diamond-like structures, aided by the intense pressures and temperatures present in the ice giants' atmospheres. Imagine tiny carbon atoms linking together under immense pressure, transforming into brilliant, resilient diamonds that fall like rain through the atmosphere. The process is incredibly efficient and sustainable within these planetary conditions, demonstrating nature's ability to create such valuable materials under extreme circumstances. This phenomenon not only sheds light on the diverse chemical processes occurring in our solar system, but also fuels our curiosity about what other wonders might exist in these cosmic laboratories. Ultimately, these discoveries remind us of the infinite complexity and beauty hidden within the farthest reaches of our solar system, waiting to be revealed through scientific inquiry. Beneath the swirling storms of Uranus, an extraordinary phenomenon occurs: diamond rain. Over time, these precious gems form and fall like crystalline showers across the ice giant's surface. These diamonds are not like those we find on Earth. They are pure carbon, forged under immense pressure deep within Uranus's interior. Imagine tiny diamonds raining down continuously, each one impacting the planet's surface with a microscopic but relentless force. Over millions of years, this incessant rain of diamonds transforms the ice giant's surface composition. The constant bombardment gradually breaks down the planet's icy mantle, enriching it with carbon. This continuous process alters not only the surface chemistry, but also the appearance of Uranus over geological timescales. The once pristine, icy landscape becomes marred with carbon deposits, a telltale sign of the diamond rain's relentless impact. As a result, the surface of Uranus may look quite different from its neighboring planets, bearing witness to the unique geological forces at play within its interior. Ultimately, diamond rain's impact on planetary surface composition serves as a testament to the transformative power of cosmic phenomena. The strong magnetic fields of ice giants like Jupiter and Saturn can generate intense planetary lightning storms, much different from the familiar thunderstorms on Earth. But what sets these ice giants apart is the presence of diamonds within their atmospheres, a phenomenon known as diamond rain. These tiny diamonds form as carbon atoms in the upper atmosphere crystallize and fall towards the planet's core. The presence of these diamonds alters the typical lightning behaviors on these planets by influencing their electrical conductivity. This discovery suggests that the electrical discharges on Jupiter are not merely a result of its magnetic field, but also influenced by the water content brought about by diamond rain. The far-reaching effects of diamond rain extend beyond simple precipitation, playing a crucial role in shaping the atmospheric electrical behaviors and lighting patterns on these giant planets. In the depths of Uranus and Jupiter, the carbon cycle takes on an extraordinary form. While carbon's journey through Earth's atmosphere is well understood, these ice giants present a uniquely complex dance. Let us explore how diamonds play a pivotal role in transporting and trapping carbon within their massive atmospheres. The process begins with methane, a significant component of these planets' atmospheres. On Uranus, for instance, methane makes up 2.3% of the atmosphere, giving it a distinctive blue-green hue. As sunlight penetrates these atmospheres, ultraviolet radiation breaks down methane molecules into carbon atoms and hydrogen atoms. This decomposition initiates a series of intricate chemical reactions. One of the key outcomes of this process is the creation of polyaromatic hydrocarbons, or PAHs. These are carbon-rich compounds that can clump together and precipitate out of the atmosphere as soot-like particles. Now, these PAHs do not remain in their soot form for long. The immense pressure and heat within the planet's interior transform them into something far more precious: diamonds. Diamonds, being denser than their surroundings, sink through the atmosphere like gemstones falling through water. This is what scientists refer to as diamond rain, a phenomenon where diamonds rain down in these planets' atmospheres. These diamonds, however, do not simply disappear into the depths of the planet. They play a crucial role in trapping carbon within the atmosphere, effectively locking it away from further chemical reactions. Observations from spacecraft like Cassini and Galileo have provided valuable insights into this process, revealing how the constant rain of diamonds shapes the atmospheric conditions on these giant planets. By understanding this intricate pathway of carbon through ice giants' atmospheres, we gain a deeper appreciation for the unique environments and processes at work in our solar system. And as we gaze upon these distant worlds, it is fascinating to contemplate that the same element that is so vital to life on Earth, carbon, plays such an extraordinary and different role in shaping the atmospheres of these celestial giants. As we continue to explore our solar system, each discovery adds another layer to our understanding of the vast and intricate cosmic dance that defines these celestial bodies. One such phenomenon is the intriguing possibility of diamond rain. Imagine this: diamonds falling like precipitation in the dense atmospheres of these distant worlds. But how do we detect something as elusive and tiny as diamond rain on planets billions of miles away? The answer lies in the subtle clues these diamonds leave behind, their infrared signatures. Infrared spectroscopy allows us to peer into the atmospheres of these distant worlds, discerning the faint signals that reveal their secrets. Recent infrared data analyses have provided tantalizing hints about the presence of diamonds in these atmospheres. As the methane-rich atmosphere is heated, it breaks down into smaller hydrocarbons like acetylene and ethane. These molecules are then believed to coalesce under extreme pressure, forming tiny diamonds. These diamonds, falling through the dense atmosphere, emit infrared radiation that can be detected by sensitive instruments on Earth-orbiting telescopes. By studying these infrared signatures, scientists can begin to piece together the complex puzzle of diamond rain and its role in shaping the atmospheres of Uranus and Neptune. Imagine witnessing this cosmic spectacle firsthand: the sheer beauty and scientific significance of diamond rain falling through the atmospheres of Uranus and Neptune. Infrared spectroscopy is not just a tool for detecting diamonds, it's a window into the dynamic processes that sculpt these distant worlds and make them uniquely fascinating. But what makes Uranus truly unique is the presence of diamonds high up in its atmosphere. As these tiny crystals rise through the atmosphere, They scatter and absorb light differently than other atmospheric particles. Observations from the Hubble Space Telescope have revealed that these diamonds significantly affect how light is scattered and absorbed in Uranus's atmosphere. This unique interaction between diamonds and light creates a visual spectacle unlike any other in our solar system. This phenomenon not only shapes the distinctive appearance of Uranus, but also offers valuable insights into the dynamic processes that sculpt these distant worlds. Planetary gravity plays a crucial role in the condensation process that leads to diamonds. The force of gravity then pulls these minuscule diamonds downward towards the planet's surface. As they fall, they can collide and merge with other diamonds, creating larger and more resilient ones. Varying gravities on different ice giants can affect both the size and frequency of these diamonds. These complex forces can influence how diamonds form and descend through the atmosphere. Imagine witnessing this spectacle firsthand. Tiny diamonds raining down, sparkling briefly before fading into the darkness. This fundamental role of planetary forces deepens our understanding of how these distant worlds are sculpted. As we delve deeper into the enigmatic world of ice giants, one of the most captivating phenomena is the formation and fall of diamonds as rain. These precious gems are not merely a testament to beauty, but also an intricate product of planetary dynamics. Seismic activity plays a pivotal role in this process. Just as earthquakes and tremors shape our own planet, similar forces sculpt the icy landscapes of these distant giants. Now, picture this. Amidst these extreme conditions, tiny crystals of carbon begin to form and grow, eventually coalescing into the diamonds we know and cherish. But the journey doesn't end there. Once formed, these precious gems must make their way to the surface. It's here where another fascinating aspect of planetary dynamics comes into play. Seismic activity can actually help propel these diamonds upwards, similar to how volcanic eruptions expel lava and ash. As the ice giants experience these internal tremors, it can create pathways for the diamonds to ascend through the planet's icy crust. Eventually, they break through the surface and fall like raindrops into space, a spectacle that, while rarely observed, is a breathtaking display of celestial phenomena. This interplay between seismic activity and diamond formation reveals an often overlooked aspect of planetary dynamics that shapes the very fabric of these distant worlds. As we gaze into the cosmos, we are not just witnessing a dance of stars, but also a complex ballet of forces that sculpt our universe in ways both profound and beautifully intricate. Consider the ice giants, Uranus and Neptune, where the atmospheric winds reach extraordinary speeds. Reaching up to 900 kilometers per hour on Uranus, these winds shape more than just the weather. They influence the behavior of diamonds in the planet's atmosphere. As the winds push and pull, they guide the fall of diamonds, determining not just where they land, but also at what rate they descend. These high-speed currents can accelerate or decelerate the descent of diamonds, creating patterns that would be nearly impossible to predict without observing them firsthand. Imagine witnessing this phenomenon, a sparkling diamond rain dancing through the sky, guided by invisible forces that carve intricate patterns into the atmosphere. This complex interplay of winds and diamonds adds another layer to the beauty and mystery of our cosmic neighbors. As we explore further, each new discovery reveals how deeply connected all aspects of these planets are, from their winds to their precious gemstones. Breathe in the wonder of a universe where diamonds can rain and winds sculpt their journey through space and time. The story of diamond rain is not just one of celestial beauty, but also a testament to the intricate forces that shape our cosmos. And as we continue our exploration, we come to appreciate the harmony and complexity of these distant worlds, one beat at a time. Planetary magnetic fields play a crucial role in the formation and behavior of diamond rain on ice giants like Jupiter and Uranus. These powerful forces guide charged particles through the planet's atmosphere, facilitating the process by which carbon atoms come together to form diamonds. This magnetic field not only generates stunning lights, but also influences the movement of charged particles in Jupiter's atmosphere. As these particles collide and condense, they form tiny diamonds that fall like rain into the planet's dense core. Observations show that the fall and distribution of diamonds on these ice giants are influenced by their magnetic fields. The charged particles, guided by these forces, create unique patterns in the fall of diamond rain. As we delve deeper into this fascinating process, another layer of understanding unfolds. The magnetic fields of these ice giants are integral to the formation and behavior of their diamond rains, providing a holistic view of this extraordinary phenomenon. With each new insight, we appreciate the intricate dance of natural forces that create such wonders in our universe. These distant worlds, with conditions far different from those on Earth, offer a glimpse into what could be a mesmerizing celestial spectacle. Observations of exoplanet atmospheres have hinted at the presence of carbon-rich environments, which are thought to be favorable for diamond rain. Theoretical models predict that under the intense pressure and heat within these planets' atmospheres, carbon atoms could coalesce into diamonds. Imagine witnessing this extraordinary process firsthand, a cascade of tiny diamonds falling like rain through the skies of an exoplanet. Though we cannot yet observe these distant worlds directly, our understanding continues to expand, revealing the potential for diamond rain beyond our solar system. The thought of such a celestial wonder not only captivates the imagination, but also deepens our appreciation for the vast and intricate dance of natural forces in the cosmos. In the heart of our solar system, two celestial bodies dance to a rhythm of their own making, Jupiter and Uranus. While we often marvel at the majestic bands of gas that envelope these ice giants, it's what lies beneath their turbulent surfaces that truly sets them apart. The intense pressure deep within Jupiter and Uranus transforms carbon into a substance as hard as diamond, a process that scientists have dubbed diamond rain. These diamonds are not the precious gems we find on Earth. They are tiny, microscopic particles that fall like rain from the skies of these distant worlds. The constant barrage of diamond rain impacts the cooling rates of these ice giants, altering their internal dynamics over time. This continual bombardment of diamonds can act as a sort of heat pump, redistributing thermal energy throughout the planet's interior. Over billions of years, this process could significantly shape the structure and composition of an ice giant's core. The sound it would make, if our ears could perceive it, might resemble a gentle tinkling, like the softest of bells ringing. This incredible phenomenon not only adds to the mystique of these celestial bodies, but also offers insights into their geological history and internal structure. To explore the fascinating phenomenon of diamond rain, scientists have conducted high-pressure and high-temperature experiments in laboratories. These artificial diamond rain experiments aim to replicate the extreme conditions found within ice giant planets like Uranus and Neptune. In these experiments, scientists subject carbon-rich materials to immense pressures and temperatures comparable to the planetary interiors. The goal is to understand how diamonds can form under these harsh conditions, providing valuable insights into the geological history and internal structure of these distant worlds. Results from these experiments have been intriguing, revealing that diamonds can indeed form under such extreme pressures and temperatures. These findings suggest that diamond rain could be a common occurrence on ice giants, adding to our understanding of these mysterious celestial bodies. By witnessing the formation of artificial diamonds in controlled settings, scientists gain a glimpse into the fascinating processes that shape the universe around us. This methodology not only advances our knowledge of diamond rain, but also highlights the scientific ingenuity used to study cosmic phenomena. Imagine standing in a laboratory, watching as tiny, glittering diamonds are born from the intense heat and pressure, offering a glimpse into the inner workings of distant worlds. Let's picture the intricate dance of planetary atmospheric circulation, a ballet of winds and currents that shape the skies of our solar system's ice giants. Imagine Uranus, with winds howling at up to 900 kilometers per hour, faster than any storm on Earth. These supercharged winds drive the planet's complex atmospheric circulation, creating currents that stretch from the swirling clouds to the distant reaches of space. In this turbulent environment, diamonds form high up in the sky and are carried by these winds, raining down on the ice giant's surface. Convection currents play a crucial role in this celestial spectacle. As warm air rises, it creates updrafts that can carry tiny diamond crystals aloft. Meanwhile, the downward flow of air helps to bring these sparkling gems back down to the planet's surface. This constant interplay of updrafts and downdrafts creates a dynamic atmosphere where diamonds can rain down. Imagine standing on Uranus's frozen plains, watching as these minuscule diamonds tumble from the sky like a shimmering meteor shower. The winds carry these precious gems across vast distances, painting the sky with a glittering trail. These winds are more than just air currents. They are the lifeblood of Uranus's atmosphere, keeping its skies alive with wonder. Uranus's winds, driven by the planet's extreme temperature variations, are more than mere gusts. They carry within them tiny particles of carbon. As these winds clash with the colder air currents, a process known as carbon deposition begins to take place. As these clusters grow denser, they begin to transform into graphite, a more stable form of carbon under such intense pressure and cold. But the story doesn't end here. The graphite, now under immense pressure, starts to undergo a dramatic change. Temperatures rise deep within Uranus's interior, creating a sharp gradient. In these hotter regions, the graphite crystallizes into diamonds. This process of carbon deposition in extreme conditions is what scientists believe creates the phenomenon known as diamond rain. Imagine witnessing this incredible event, tiny specks of graphite transforming into sparkling diamonds, raining down through Uranus's atmosphere. These tiny, brilliant gems rain down through Uranus's skies, a testament to the wonders hidden within our solar system. The formation of these diamonds is not just a marvel, it also offers insights into the conditions necessary for life elsewhere in the universe. These tiny, sparkling gems are more than just beautiful objects. They are clues to the mysterious processes that shape our cosmic neighborhood. The unique properties of diamonds on ice giants like Uranus introduce intriguing complexities into the planet's electrical dynamics, particularly when it comes to planetary lightning. Diamonds are excellent insulators, but under the right conditions, they can become conductors of electricity, setting the stage for dramatic atmospheric events. This ionization process turns these tiny gems into charged particles, which can then participate in powerful electrical discharges. Imagine the spectacle, a storm on Uranus unleashing bolts of lightning that contain diamonds raining down through the atmosphere. These electrical interactions not only shape the planet's atmospheric dynamics, but also influence the formation and descent of diamond rain, creating a cyclical process that defines Uranus's stormy environment. The interaction between diamonds and lightning on ice giants is more than just a mesmerizing sight. It offers insights into the intricate workings of these distant worlds. Thermodynamics is the science of energy and heat transfer in systems. The upper layers of these planets can be as cold as 217 degrees Celsius, 358 degrees Celsius, while deeper layers are significantly warmer. This extreme temperature difference drives the process of diamond formation. Carbon in these atmospheres begins to crystallize as the temperature drops. Under immense pressure and cold conditions, this carbon transforms into diamonds. Cooling and high pressure are key elements in the thermodynamic processes that make diamond rain possible. Imagine witnessing this spectacle. diamonds forming under extreme conditions and then falling like rain through the thick atmosphere of an ice giant planet. Understanding thermodynamics helps us grasp how diamonds can rain from the skies on planets far beyond our own solar system. To understand how diamonds rain from the skies on certain ice giants, we first need to explore their atmospheric composition. The presence of these gases sets the stage for a unique phenomenon, the formation of diamond rain. Under extreme conditions, the methane in their atmosphere can react with hydrogen to form complex carbon compounds like acetylene and ethane. As these compounds rise higher into the atmosphere, they encounter even colder temperatures. At these frigid heights, the carbon atoms in these compounds begin to solidify and crystallize into tiny diamonds. This remarkable process is made possible by the unique atmospheric conditions on these icy worlds. With a better understanding of their atmosphere, we can begin to appreciate the beauty and complexity of these distant planets. Beneath the swirling clouds of Uranus and Neptune, a phenomenon occurs that defies earthly imagination: diamond rain composition varieties. These diamonds do not form in the fiery furnaces of terrestrial mines, but rather condense out of the carbon-rich atmospheres of these ice giants. The atmospheric conditions on these planets, with their high pressures and low temperatures, provide the perfect environment for diamond formation. Diamonds are not all alike. They can vary significantly in composition, depending on the source of carbon. Type Ia diamonds, for example, form from carbon that was once part of a star and was later released into space through stellar explosions called supernovas. These diamonds contain trace elements that were present in the original star, giving them unique properties not found in other types of diamonds. In contrast, Type II diamonds form from pure carbon sources, such as methane gas in the atmospheres of these ice giants. Because of their pristine origin, these diamonds are typically devoid of impurities and possess a brilliant, flawless appearance. As these diamonds fall through the dense atmospheres of Uranus and Neptune, they accumulate in vast quantities, creating stunning displays of gemstone rain. Imagine witnessing this spectacle from a nearby observation post. The sight would be breathtaking as these gleaming gems cascade down like liquid silver. The beauty and complexity of diamond rain composition varieties highlight the extraordinary phenomena that occur in our cosmic neighborhood. Although diamonds are known for their sparkle on Earth, they serve a different purpose in the atmospheres of ice giants. The presence of diamonds can significantly influence a planet's albedo, a term that refers to how much light a surface reflects. Planetary albedo is essential for understanding how ice giants regulate their temperatures and atmospheric conditions. In simple terms, a higher albedo means the planet reflects more sunlight back into space, which can help keep the planet cooler. This scattering effect is not uniform across the spectrum. It varies depending on the wavelengths of light. Diamonds are particularly efficient at reflecting visible and ultraviolet light, which can have a profound impact on the planet's overall albedo. In regions where diamond rain is prevalent, Uranus might appear brighter than in areas where there are fewer diamonds. This uneven distribution of reflectivity can lead to complex patterns of heating and cooling across the planet's surface. The varied albedo caused by diamond rain contributes to Uranus's extreme weather conditions. The tilted magnetosphere and the uneven distribution of diamonds create areas with different reflectivity, which can lead to significant temperature variations. Understanding these dynamics is crucial for gaining insights into the larger climate systems of ice giants. While we may not be able to witness diamond rain on Earth, studying its effects on Uranus and Neptune offers a glimpse into the fascinating interplay between atmospheric particles and planetary reflectivity. The intricate dance of diamond rain and its influence on Uranus's albedo highlights the beauty and complexity of our cosmic neighborhood. As we continue to explore these distant worlds, each new discovery deepens our understanding of the universe's diverse and awe-inspiring phenomena. Within the vast, swirling interiors of ice giant planets like Uranus and Jupiter, a complex dance of carbon transport is at play. This dance is essential for the formation of diamonds within these distant worlds. Convective currents within these planets play a crucial role in this process. These currents act like a giant mixing bowl, stirring carbon-rich material from the atmosphere down into the icy mantle. Imagine this process as a slow, ceaseless churning. Over time, these currents distribute carbon throughout the planet's interior, laying the groundwork for the formation of diamonds. Additionally, atmospheric mixing on ice giants helps to disperse carbon evenly throughout their environments. This ensures that a steady supply of carbon is available for the formation processes within. The unique tilt of Uranus's magnetic field further influences these dynamics, creating unusual patterns in the movement of carbon-rich materials within its interior. This intricate dance of carbon transport not only aids in the creation of diamonds, but also shapes the internal structure and composition of these distant worlds. Witnessing this process firsthand would reveal a planetary ballet carbon transported by massive convective currents and atmospheric mixing, ultimately leading to the birth of diamonds deep within these cosmic giants. Understanding this complex carbon transport is vital for unraveling the mysteries of diamond formation in ice giant planets and deepening our appreciation for the cosmic marvels around us.